Hello, this is Mr. Gilmore with the 1.2 matrices lesson. So today is really where the work of our linear algebra system begins. We introduce this concept of what we call a matrix or plural matrices. And what we'll be finding is we'll be working with the elementary attributes of a matrix for a long time, many chapters. But then towards the end of our semester, with the chapters we'll be progressing through, we'll experience some abstraction of matrices. So today we're going to introduce what a matrix is, what that looks like. We'll look at some examples of matrices, and then we'll look at several some of the initial basic properties of matrices, and we'll continue talking about some other basic properties of matrices as we continue the next several sections. Let's start with what is a matrix. A matrix is a rectangular array of mn real or complex numbers arranged in m horizontal rows and n vertical columns. Down below is an example of this. We have those are a lot of dots going on in there, but each of those little dots represents that we can actually continue the number of elements in each row, or continue the number of elements in each column to actually find a location, basically, and we can arrange our data within inside of this, what we call matrix. So there are m rows and n columns, which leads to a total of mn real or complex numbers. We'll typically still stick with some real numbers. We'll see some examples that show up early on that use some complex numbers, and then as we move towards some abstraction, we'll see more complex numbers show up. So we will typically use, and this is actually a standard. Most textbooks do this. Typically use m as the number of rows and n as the number of columns. And then also, if we're referring to a specific row or specific column, we use the letter I for the ith row, and then we use the letter J for the jth column. So we can talk about the ith j element, which is actually the element that's in the ith row and the jth column. So, for example, in the first row and first column, we see that we have an element a sub 1, 1. So don't read that as a sub 11. Read that as each individual subscript as being what row it is at first, and then what column it is in. So it is row 1, column 1, so a sub 1, 1. Then the next element to the right would be a sub 1, 2, because now we're still in the first row, but now we've moved to the second column. If we go all the way to the end, we're at the nth we're at the nth column, right? Because there's n vertical columns. So nth column, so that would be the a sub 1 n nth element in our matrix here. And then if we continue down the column, let's say we go down the column. So let's go back to a sub 1 1. We then find a sub 2 1, which is now we've moved into the second row, first column still, and we continue all the way down. There are m rows, which means we arrive to the a sub m1, which m is the mth row, but we're still in the first column, and that's how we're going to be using our subscripts to actually help us denote our arrangement of our elements that we find within our matrix. Now, typical matrices. You can have any number of integer values for m and n. If we find that m and n are the same value, that they are equal to each other, we call this a square matrix. Essentially, we'll put this in terms of n, and we'll say that A is an n by n matrix, meaning it's going to be a square matrix. And we'll see as we progress throughout this several units, we will see a variety of different size matrices. However, we will focus on the square matrix. We find a lot of good uses within the square matrix as we progress through our lessons. One other quick note is if we continue within a square matrix, we'll look at this an example in just a second. If we look at the elements that are in the their subscripts have the same value, so like a sub 1 1, a sub 2 2, a sub 3 3, so on until it's a sub n n. Those are actually what we call, they form the main diagonal of a square matrix, and you'll read that in the textbook. And then if we were to refer to each element inside there, we call it, we can refer to it as either one of two ways. We can call it the ijth element, or we can simply, as an ordered pair, write it as an ordered pair I comma j entry, or I comma j element. So either way refers to the element within inside. This is the typical way we see the element being shown within inside of a matrix A sub I j. And we can also simplify this matrix. We don't need to write this out the entire time. If we're defining a matrix A, one of the standard ways of doing this is just simply writing out that ijth element and saying this is a matrix. And so I can be anything from 1 to let's see, that's our row. So 1 to m, and then j could be anything from 1 to n. And then that would, of course, then define any number of rows and any number of columns that we need within inside of our matrix. Okay, so let's look at some examples of matrices. Here are several. We have 4 matrices here, A, B, C, and D. A, we see, is a 2 by 3 matrix, right? So we actually, we denote this with first by the number of rows, and then we use this multiplication symbol. It's kind of like the word by, right? If you're thinking about like a construction, right? 2 by 4 or whatever. This is a 2 by 3 matrix is how we would read that because we have 2 rows and 3 columns. We always read off the rows first and then the number of columns. So B is actually a square matrix because that is a 2 by 2. It has the exact same number of rows and columns. C would be a 1 by 3 matrix, and then D would be a 3 by 1 matrix because there are 3 rows, but there's only 1 column. Now, go back to matrix B real quick. I mentioned this main diagonal. The main diagonal would be this set of numbers right here, 3 and 10, because they are along the main diagonal of their subscripts are the same, A sub 1, 1, and then A sub 2, 2. And we can continue that if we had a matrix which had three values. A 3 by 3 matrix, which means we would have 3 values in the main diagonal. All right. One quick thing too, as we take a look at these matrices, one question we may have would be, how do we put this into our TI-89? That's a great question. We actually can store matrices into our TI-89 and then use our store function to place that into some alpha variable, and we can actually recall that variable using some of the functions we would like to use throughout the semester as well. So how do we store them into a TI-9? Let's say we are given a matrix E, and that matrix E is simply this is a 1 by 3. So 1, 2, and 3 are the 3 elements in there. How we would store that into the calculator is we would use these square brackets, the square brackets here, and then we would have 1 followed by a comma, 2 followed by a comma, and 3, and then close it out with the closed square bracket. And that actually we could store into the calculator. So this is what it's going to look like. That's what you're going to type in to the TI-89 there. And that will actually, if you hit enter with that, it will show this when you hit enter on the display screen. Okay, but what if I wanted F? So E was a 1 by 3, but F is a 3 by 1. How do I then denote their different rows? Well, we use semicolons to denote different rows. So commas give us separated columns. So 1, 2, and 3 are different columns, but the semicolon gives us different rows. So if I were to type 4 semicolon 5 semicolon 6 and then put my open and closed brackets, square brackets on the front and the back, and I could store that if I wanted to as well. If I hit enter, it's going to then spit that out. It's going to show me that. So remember, so semicolons, that looks like a J. Hold on, give me a second. Actually, a comma. Oh gosh, I'm really bad at this. Comma is a column. That's easy to remember. Comma, column. And then a semicolon. I'm really bad with semicolons. Here we go. That's a semicolon, and that is row. Okay, that separates the rows. All right, so now, so comma is for column, and then semicolon is for row. And I really wish I could draw semicolons well. Let me just try this again. Hold on. Here we go. Oh, that's so bad. Oh, this is so bad. There we go. That's a bit better. I feel better about that one, but it's not the best. Anyway, last example here is G. Let's say we have a square matrix here. 7, 8, 9, and 10 are my elements, which means I need 2 elements in my first row, but I need 2 rows, and then I need 2 elements in my second row. So how I would do that is I would type 7 comma, right, because that's my column separator. So 7 is a column, 8 is in a second column, but then I do another row and I put a semicolon in there. And then I have my other 2 elements, 9, comma 10. 9 followed by the comma means I'm moving into the next column, right? So comma comma columns, semicolon rows, right? All right, so that's how, if I were to actually type this into my TI-9 and hit enter, it would spit that thing out right there. And of course, I could store that into some alpha and recall that alpha if I need to, if I'm using any sort of function. And we'll see, we'll make use of stored matrices in our TI-9s down the road. All right, let's talk about n vectors. We've talked about vectors before in multivariate. You've probably talked about vectors within physics before, but we also have what are called vectors in a matrix form. And an n vector is an n by 1 matrix, meaning we're looking at storing our elements in the rows, not in the columns, right? So it's going to be stored in one column, but we're going to store each of our vector components into each individual row. And so the n is, again, just the number of elements that we'll find in each vector. And how we denote a vector in typeset, we would use a lowercase boldface letter, but in written script, we would actually use our vector notation, which means we'd put the little arrow above. So down below, it's a bit redundant. I do have the vectors bolded and have the vector notation above. I really just need to have them bolded since it's in the typeset, but I just wanted to show you what the vector notation was in case you forgot what that looks like. And I wouldn't have to, if I'm writing that out, I wouldn't have to bold that out. If I'm writing it out, I just write U with the vector notation over top. So the first example there, U is a 4 vector, which means it has 4 elements, and I would list that out and with 4 rows, 1 element in each row. So 1, 2, -1, 0 is what that is defined as right now. I also have a V vector, which is a 3 vector, and I can have any number of elements. With I can have a 1 vector, a 2 vector. We even can have a 0 vector. A 0 vector, when we talk about a 0 vector, a 0, I should say a 0 n, a 0 vector with this n notation, it really then is a n vector such that all the entries are 0. All right, which means I can add the 0 vector, to any of my other vectors, and it would just give me that same vector back. So if I took U, this U vector here, this 4 vector, and added it to the 0 vector then inherits the property of 4, which means it's going to have 4 elements of 0. And I add 0 to it, which means it's just really the same thing. So just keep that in mind, that there are 0 vectors as well that we can work with when working with matrix, or with these n vectors. Now, matrices. We can use matrices to do a lot of things with. We can store data in them. Maybe there is an example where you are analyzing a product that 3 different companies make, and maybe you're looking at these 3 companies make 4 similar products, and you're comparing some sort of data that you bring the 4 products with these 3 companies, and you want to store them in a matrix form. So you could have maybe your companies along the rows, and then each of the 4 products along each column. And so you'd have a 3 by 4 matrix where each row stores the company data for each then of their 4 products that they make. Maybe it's production, maybe it's weight of the object, maybe it is quality of it, maybe it's a user rating of it. It could be anything that's stored within inside that matrix. In fact, a lot of internet websites use matrices to store data because it's then easier to then collect that data, and then also if it's going through some I don't know, meta algorithm, you can operate on that matrix, and we'll talk about matrix operations too. Google uses what we call an incident matrix. What an incidence matrix is basically, imagine a matrix where the only entries can be 0 and 1, and the matrix would be a square matrix. And what you'd have is you would have maybe a search word on the left, and then some linked site, a search word for the rows, and then you have some linked site for the columns. And every time that maybe that word is associated with then that site, then the value stored at that ith, jth element turns into a 1, meaning there's some link between that search word and that website. Or it could be a 0, which means that if that one stored word is not actually associated with that website. And of course, over the many now decades that Google's been around, the incidence matrix has been developed and honed, and different algorithms have been applied to it. And of course, we're talking in the billions now, even closer, probably trillions sized incidence matrices. And of course, you need a better way of managing those. So Google's, worked with many different mathematical ways of storing that data. Um, because a lot of times, if you go to the search engine, you want to search something, you want it to actually find something that's relative to what you searched. And that's how that incidence matrix would actually help. Okay, so like matrices or like any sort of elements we've worked with in mathematics, we will find some of the basic properties do apply to the matrix. For example, we have matrix addition, and how we find that is let's define two matrices to start us off with. Let's call them A and B, and the only way we can actually add matrices together is they have to be the same size, meaning they have to be the same dimensions. So they have to both be an m by n matrix, where m and n are obviously the same values. You can't take a 2 by 2 and add it to a 2 by 3. That doesn't actually work. It had to be a 2 by 3 plus a 2 by 3. That would work. And so we can actually add A and B together to find a new matrix. We'll call that matrix C, such that the elements in C are really then just the sum of the elements within A and B. So we take A sub ij, which is the ijth entry, and ijth entry of B as well. And we add those entries together to form then the entry for the C matrix. And I and j can be, again, remember, they're anywhere between 1 to m rows and then 1 to n columns. So an example down below, we have matrix A and matrix B. Uh, We're going to add these matrices together. Notice they are the same size, 2 by 3, 2 by 3. So what we can do is I just simply then move to take each element in their respective location. So the A sub 1, 1 plus B sub 1, 1, which is our element of 1 and element of 0. I add those together, and they form the element for our C matrix. I do that with each respective element location within inside of our matrix, and of course then we can form a new matrix. So you see down below I have my operations laid out of what it looks like. Let's say if we're looking at the second row, let's do the second row, second element. That means our A sub 2 2 is -1, and B sub 2 2 would be 3. So I take -1 plus 3, it turns into 2. And then there we have our output, right? The sum of our A plus B, the output of that matrix is 2 by 3. We get our elements of 1, 0, 4, and then 3, 2, 0 would be our corresponding elements for matrix C. And that's how matrix addition works. Very simple. Okay, scalar multiplication. We can take any matrix and multiply it by some real value, some scalar value. So let's let that scalar value be R. Again, the matrix A could be any size. It doesn't matter what size matrix this is. So we'll call this an m by n matrix. And what we're going to do is take R and multiply it to that matrix. And essentially what that means is we're going to form a new matrix. We'll call that new matrix C. And that new matrix C will have the ijth element of C be equal to R times the ijth element of A, right? So A's ijth element for each is just simply be multiplied by R. And that again, I and j can be anywhere from 1 to m rows and 1 to n columns. So down below is an example. We have matrix A being defined as this 2 by 3 matrix, 4, -2, -3, 7, -3, 2. And we're going to multiply by the scalar -2. So now I simply just think of it as like a big distributive property where you're going to take that -2 and you're going to multiply every single element in A by that -2. And we get -8, 4, 6, -14, 6, and then -4 to conclude our scalar multiplication. What this also then means is we can understand matrix subtraction as well. So really, matrix subtraction is really just it's a addition of a -1 scalar being multiplied to some matrix. So A minus B down below, the difference of A and B is really equal to A plus the scalar -1 times B. So we would distribute that -1 through each of the elements of B and then add that to A. And that's, of course, assuming that A and B are the same size. So that's always one of the big assumptions we would make if working with some sum or difference of matrices. Now, you will see some homework questions where I'll ask you, hey, add these together, and you may not be able to because they're not the same size, and that's okay, right? If I say, hey, add these together, you're going to say, hey, not possible. Okay, they need to be the same size. We have to have the same rows and same columns, same dimensions. All right, linear combinations. We can actually basically take matrices and we can form them into some linear combination of itself. So let's say we had a matrix A, and we've defined then other matrix A. So we have A sub 1, A sub 2, all the way to A sub k. And they're the same size of our matrix A. We'll call those M and N, or M by N matrices. And we've got these k amount of real numbers. So C sub 1, C sub 2, and all the way up to C sub k. Which, remember, we can multiply now our scalars into into a matrix. Well, what we can do is we can actually form a linear combination of any matrix by simply breaking that matrix down into a scalar times any submatrix. So, or sorry, not submatrix, but a matrix store with maybe a different elements in it. So C sub 1 times A sub 1 plus C sub 2 times A sub 2. This is what we call linear combination. We will find out in our next lesson a breakdown. We'll be actually using linear combinations to break down matrices in the next lesson. And so just as a quick example what this would look like, I have the C sub 1 and C sub 2 elements being 3 and negative 1/2. So those are our scalars. And then my A sub 1 and A sub 2 would be our first and second matrix that we see there. They're both 3 by 3s, which means we can add these together. So essentially, these will then simplify down to a single 3 by 3 matrix with no scalar in front. And that's going to give us our resulting matrix. But sometimes, in many cases, the resulting matrix that we are given, or if we have, it may be harder to interpret with the state that it's in. So in some cases, it might be easier to take a given matrix and break it up into a linear combination of scalars and some other matrices that will, when we multiply and add back through, result in that given matrix. However, we'll find that some of the strategies will be to take a given matrix and break it down into some other easier elements to work with. And we'll talk about those as well in the future. Last little bit about matrices, we can actually, what's an operation called the transpose of a matrix. We actually can, what we're going to do with a transpose matrix is first let's define a matrix A. Let's let that be an M by N. And what we're going to find when we transpose A, which symbolically looks like we have the capital T as an exponent. So we have our matrix A raised to the capital T. So what that looks like, that's just our symbolism we use to denote that this is the transpose of our matrix. We're going to basically take our matrix and turn it into an N by M matrix. So notice that it was an M by N, and we basically flipped the dimensions. So there were originally M rows and N columns. We're now going to make it N rows and M columns. And what that does is, meaning when we apply the transpose to each element, we reverse the order of their subscripts. So if the subscript was 1, 2, let's say it was the first and the first row, second element of the second column element, we reverse that to A sub 2, 1. So if it was A sub 1, 2, it turns into A sub 2, 1. So basically, down below, I've given some examples of some of transpose of matrices. Basically, here's the easiest way to do this. You take each row and the elements in that row, and then you rewrite them as the column, the first column. So if I'm looking at A, I take the first row, which is 4, negative 2, 3, and I'm going to then re-express that as a column. So I'm going to write that first column being 4, negative 2, 3, but as a column. And then my second row of A is 0, 5, negative 2. Now in my transpose, I will then write that as the second column. So it becomes 0, 5, negative 2. So again, it goes from a 2 by 3 to a 3 by 2 matrix. B is a square matrix, which means it'll still remain a square matrix when we transpose it. And you'll notice that our main diagonal stays the same. That's actually an interesting thing when we transpose. The main diagonal stays the same. 6, negative 1 is on our main diagonal. But then the components, the elements in our A sub 1, 2 and our A sub 2, 1, they flip. And then you'll notice that in our transpose of B, that 2 moves to 3 and 3 moves to 2. You'll see that transposing square matrices is not that bad. Our last example there is our matrix C, and matrix C is a 3 by 1, which means it's going to become a 1 by 3. So 3 by 1, I take that column, right? Take that column and just make it a row, right? So now make that column into a row and becomes 2, negative 1, 3 as a row. We'll see the use of this operation on our matrix transpose in our next lesson when we talk more about some of the properties of matrices. We'll talk about the dot product, and we'll now talk about matrix multiplication. What does it actually look like when we multiply matrices together? That's actually a real treat for us here in the future. Other than that, that is all we have for this lesson. Please be sure to check out Canvas for the problem set that I would like for you guys to work on. If you guys, of course, have any questions, do not hesitate to email me with that. Be good and do good.